Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Our mission impossible is simply to convert some of the hate energy into love energy for mathematics. As your screen indicates, like it or not, math really did take us from the Stone Age to the Space Age. Now let's get down to some serious math. This will be video number 4 on the continuing series on exponents and, of course, exponent laws. We're going to look at the next question over here, Q1, and it says using exponent laws to simplify expressions with whole numbers only. Okay, so that's what we're going to be doing. Let's look at Q1A. When we look at this expression carefully, we'll notice a dot there, dots everywhere. So this constitutes one cluster, single cluster. And also, if we look carefully, we'll notice the bases are 2, 4, and 8, and 16. So we have 2, 4, 8, and 16 are the bases. And of course 2, 4, 8, and 16 has the lowest common base of 2. And that's the key to simplifying an expression such as this right here. The objective is to use the lowest common base to re-express all these bases in terms of base 2. Okay, so let's look at the next step over here. 2 to the negative 2 is already in terms of base 2. So we just drop it down. If we look inside the brackets, 4 needs to be converted. It can be rewritten as 2 to the power 2. 2 to the minus 3 is good to go. Just drop it down. The 2 has to be dropped down. The 8 can be written as 2 to the power 3, and that's all to the power negative 1. And of course, 16 can be written as 2 to the power 4. And now we have a common base of 2. So we have a single common base of 2. And we know how to do these. We've done plenty of these before. We open up a base 2 in the next line. We scan and drop the exponents. We pick up negative 2 here, drop it down. Then we have 2.2, which is 4, drop it down. And we get minus 3.2, which is minus 6, drop it down. And 3.1, which is negative 3, drop it down. And finally, we get a 4 and drop it down. So essentially, what we've been doing over here is using all the laws simultaneously. And that's really the best way to deal with exponent laws. Never think that you're going to use one law at a time, because that's very tiresome. It's very long-winded. It takes many, many steps. There's no need to do that. The entire mission is to use the exponent laws, to be good enough at using the exponent laws simultaneously. Okay, so doing little steps at a time, all you're going to do is increase your chances of making errors and going from one line to another, because your solution is going to be much longer than it really needs to be. And the longer your math solution is, the higher the chances that you're going to make errors along the way. So you want to try to avoid that. You want something nice, neat, short, sweet, which illustrates all of your work, but at the same time, it's like very concise, precise. You don't want any superfluous steps. You want to make the procedure as tight as possible. So over here, we're left with an integer string in the exponents. When we evaluate the integer string, you should certainly know how to do this by now. We get an exponent of negative 3. Now, because we have a negative sign in the exponent, what we can do is downshift, and we get 1 over 2 to the power 3. And then we evaluate 2 to the power 3, it becomes 8. So the final answer is 1 over 8. And this has all been verified. Let's go on to the next slide. This is part B. So again, the same sort of problem. To give you another shot at it, we look right across. We identify a single cluster. They're full of dots over here. There are no pluses or minuses aside from the exponents. The exponents don't count. But regarding there are no pluses or minuses in the main floor, if you will, of the product string. So we identify this as a single cluster. That means that we can use all the exponent laws simultaneously. Now we scan for types of bases that we have. We have base 2, base 3, base 4, base 8, base 3, base 27. Okay, if we look at the bases 2, 4, and 8, we know that the lowest common base is 2. Why is that? Because 4 and 8 can be expressed as 2 to the power 2 and 2 to the power 3. Next, we look at 3 and 27. The lowest common base is 3. Why? Because 27 can be rewritten as 3 to the power 3. So the key to solving a problem like this is to aim for the lowest common base, which is 2 in this case and 3 in this case. So we're going to proceed. 2 to the minus 1 is already in terms of base 2. 3 to the power 2 is ready to go. 4 can be rewritten as 2 to the power 2. The negative 1, you have to drop it down. 8 can be rewritten as 2 to the power 3. The negative 2, you drop it down. And 3 to the power 3 is good to go. And of course, the minus 1, you have to drop down. 27 can be rewritten as 3 to the power 3. Now you look carefully at the expression on the left, and we really do have only base 2 and base 3. And that's all we have to deal with, and we've done this before in the past as well. We're going to be dealing with one base at a time. I always choose the lowest base first, so the lowest base is base 2. And what we're going to do is scan the exponents only for base 2 exponents. So we get a negative 1 from here, drop it down. 2 dot negative 1 is negative 2, drop it down. And 3 dot negative 2 dot negative 1. Okay, so be careful. You have to do 3 dot negative 2 dot negative 1, which will give you 6, drop it down, and we're done with base 2. Now open up base 3. Let's scan the exponents for base 3. We get 2 dot negative 1, which is negative 2, and then 3 dot negative 1, which is negative 3, and then the 3 is a simple drop down. So again, we have base 2 with an integer string for the exponent, and we have base 3 with an integer string for that exponent. And of course, you know what to do now. You just look at each integer string and simplify it. We get negative 1 minus 2 plus 6 is 3, and negative 2 minus 3 plus 3 is negative 2. At the end, you know that you've got 2 cubed over here, which is fine, but 3 to the power negative 2 gets downshifted. And so we rewrite that as 2 to the power 3 on top and 3 to the power 2 on the bottom. 2 to the power 3 is 8, 3 to the power 2 is 9. 8 over 9 is a proper fraction in reduced form. And so we're done. Let's go over to the next sheet. Let's look at C here. Again, we have a single cluster because we see nothing but dots in the numerator and nothing but dots in the denominator. So clearly, single cluster. That means we can apply all the exponent laws. We just have to be careful, that's all. If we look at all the bases, we get a base 2 here, base 5, base 3, base 3, base 4, base 25, base 4, base 2, base 25, base 9. And we conclude that the lowest common bases there are 2, 3, and 5. 2, 3, and 5. And in the next line, we're going to express all the bases in terms of either base 2, base 3, or base 5. Notice that 2, 3, and 5 are prime bases. They're prime numbers. And that's really the objective, is to use prime numbers to work out the problem. Okay, so let's continue. 2 to the power negative 2, just a drop down. 5 to the minus 1, drop down. 3 to the power 2, drop down. Negative 1, drop down. This is just a drop down. 4 can be rewritten as 2 squared, all to the power negative 1. 25 can be rewritten as 5 squared, and of course -1 just gets dropped down there. Let's scan the bottom. We have 4 can be rewritten as 2 to the power 2, and over here 2 to the power 2 is a drop down. 25 can be rewritten as 5 to the power 2, and 9 can be rewritten as 3 to the power 2. Now if you look at the expression, everything is in terms of either base 2, base 3, or base 5, and that's the objective. So in the next line, we're just going to simplify further by using all the exponent laws. If we scan only for base 2 exponents carefully, only base 2, one base at a time, there's a base 2, we get a -2 dot -1, which is 2. Drop it in. Over here we get 2 dot -1 dot -1, which is 2. Drop it in. On the bottom we pick up a 2, becomes -2. On the bottom we get 2 dot -1, which is -2, becomes +2. Next we scan for base 3 exponents. Over here we get 2 dot -1, which is -2. Drop it in. And over here we get -1 dot -1, which is 1. Drop it in. And on the bottom, there's the base 3 right there. We get 2 dot -1, which is -2. But because it's on the bottom, it becomes +2. That would be the quotient difference law, okay? And, sorry, that was base 3 we were doing. The final base is base 5, so we just scan for base 5. -1 dot -1 is 1. Drop it in. Over here 2 dot -1 is -2, drop it in. And over here 2 dot -1 is -2, becomes +2. And now it's really becoming simple at this point. We have the prime bases 2, 3, and 5, and we have an integer string for each base. This simplifies to 2 to the power 4, dot 3 to the power 1, dot 5 to the power 1. And then 2 to the power 4 is 16, 3 to the power 1 is 3, 5 to the power 1 is 5. And then we have a product at the end. Evaluate the product to get 240. Okay, so this whole mess over here, if you use the exponent laws properly, it'll come out to be 240. And you'll have to admit we did that fairly rapidly. Don't take a lot of steps. If you take too many steps, you're going to make mistakes along the way. I don't know how much more to emphasize that. Too many steps in mathematics is not really a good thing. What you want is to have as few steps as possible, but each step has to count. The solution has to be lean and mean. No fat. Anyway, let's go on to the next slide. Here's Q2, and essentially we're going to be using exponent laws to simplify expressions with integer coefficients and variable bases. Okay, if you look at this mess over here, it looks like a real mess, but it's actually quite easy. -2 is called a coefficient because it's a number that appears out front. 4 is called a coefficient. -8 is called a coefficient. The variables are A, B, C. You see A, B, C in here and A, B, C. And the variables are all bases, and the coefficients are actually bases as well, except they're numerical values and the other ones are variables. The exponent laws still apply. No problem whatsoever. Now, in this case, all the exponents have to happen to be integer exponents. We could encounter cases as well where instead of integer exponents, we have variable exponents as well. So you can have all kinds of scenarios, okay? And what we're going to do is do a lowest common base over here. Before I continue over here, you'll notice that we have a dot here, and everything is full of dots. There are no pluses or minuses. That minus doesn't count because that's a multiplicative negative sign. That minus doesn't count. It's multiplicative. Okay, there are no plus or minus separators, therefore this is one cluster. It's a single cluster. It looks like a bit of a monster, but it's still a single cluster. We're going to be dealing with the coefficients first and then the variables in turn. We look at the coefficients. Forget about the minus sign. The coefficients are 2, 4, and 8. The minus sign is irrelevant, as you'll see in a minute. Not that it's irrelevant. We'll take care of that, no problem. We'll do a neg count to take care of that. But if you look at 2, 4, and 8, the lowest common base is 2. And then, of course, you've got the variables A, B, and C everywhere. So you declare those to be the lowest common bases, 2, A, B, and C. Okay, so the first thing I do is rewrite 2, 4, and 8 all in terms of base 2. Of course, negative 2 is just negative 2. And 4 becomes 2 squared. Negative 8 becomes minus 2 to the power 3. So no problem there. Everything else was a drop down. I didn't touch anything else. Now you're in a position to use exponent laws. Now, watch very carefully. Do you see the minus sign here and the minus sign there? We're essentially going to do a neg count for this cluster. That minus sign occurs twice, and that minus sign occurs once. So altogether, the minus sign occurs 3 times. Okay? Or the way I do it over here is I consider the minus sign to really be another base called negative 1. So let's adopt that stance that the negative sign really means negative 1. If that's the case, then we have negative 1 over here, all to the power negative 2, and negative 1 over here, all to the power negative 1. So altogether we have negative 1 to the power negative 2 minus 1. Okay, no problem there, because the minus sign can always be written as negative 1 dot. Negative 2 can always be rewritten as negative 1 dot 2. And negative 2 cubed can always be rewritten as negative 1 dot 2 cubed. Okay, so that's where the negative 1 to the power negative 2 minus 1 comes from. Then we deal with the 2. If we look at the 2, we pick up negative 2 here, and then we pick up a 2 dot 3, which is 6. So we dropped in a negative 2 and then a 6. And then over here, 3 dot negative 1 is negative 3. And we've taken care of base 2. Next, we'll take care of base A. If we focus only on base A and we collect exponents for base A, negative 2 dot negative 2 is 4. So we drop in a 4. Over here, negative 4 dot 3 is negative 12. Drop in a negative 12. And 2 dot negative 1 is negative 2. Drop in a negative 2. And we're done with base A. Next, we'll focus on base B. And we'll scan the expression only for base B. Over here, we'll pick up a 3 dot negative 2, which is negative 6. Over here, negative 2 dot 3, which is negative 6. And over here, negative 1 dot negative 1 is 1. So we drop in a plus 1. The last base is base C. So we're going to scan the expression only for base C terms. Over here, we pick up negative 2, drop it in. Over here, we pick up 3, drop it in. And over here, 0 dot negative 1 is just 0, and we can drop it in. Okay, a little note before I continue to simplify this. Whenever you see negative 1 to an odd exponent, that means there are an odd number of negative 1s. If there are an odd number of negative 1s, certainly the result is negative 1. Okay, that follows the neg count rule. Okay, and if you have negative 1 to an even exponent, following the neg count rule, that becomes positive 1. Like, for example, over here, if you have negative 1 to the power 3, that really means negative 1 dot negative 1 dot negative 1. The neg count would be 3, and the result is negative. And, of course, 1 dot 1 dot 1 is just 1. On the other hand, if you had negative 1 to the power, let's say 4, that really means negative 1 dot negative 1 dot negative 1 dot negative 1, 4 times. How many negatives? 4 negatives. And so the neg count is 4, and 4 is even. The result is positive. And then 1.1.1.1 4 times is just 1. Okay, so this is a very important rule to invoke whenever you have an opportunity to invoke it, okay? And the odd even stuff, even like negative numbers can be odd as well, like -3 is odd and -4 would be even. So the even odd stuff, they don't have to be positive numbers, they could be negative integers as well. Okay, like in other words, the odd integers would be like -3, -1, 1, 3, etc. And then you can have like -2, 0, 2, etc. for the evens over here. Okay, so let's continue to work out this problem over here. -1, this becomes -1 to the power of -3. This becomes 2 to the power 1. These are all integer strings. I'll leave it up to you to work them out. They're all fairly simple. So we get 2 to the power 1. Over here we get a to the power -10. Over here we get b to the power -11. And finally we get c to the power 1. Okay, using this even odd rule over here, -1 to the power -3 is certainly a minus sign. And that's why we have a minus sign over here, because it's -1, but of course -1 dot anything is really the same as minus anything. Okay, so -1 dot an apple is really minus an apple. And then we have 2 to the power 1 is 2, no problem. A to the power -10 gets downshifted because it has a negative exponent. B to the power -11 gets downshifted, and c to the power 1 is just c. So altogether we have a minus sign out front. We get a 2c on top. We get a to the power 10 dot b to the power 11 on the bottom. And we are done. So that real mess over here converted to something fairly simple at the end. And that's the sort of thing you need to learn how to do. Let's go on to the next slide. Part B, the same sort of thing. It gets even a little bit more messy. Again, we have a big division bar over here. We have nothing but dots on top, nothing but dots on the bottom. We declare this whole mess over here to be a single cluster. And if we look at the coefficients are -3, -9, 27, and -81. And if we look at this carefully in terms of the coefficients, the lowest common base is 3. And then the variables, we have x, y, and z. So the bases we're going to be using to simplify this problem will be 3, x, y, and z. So we'll go on to the next line. The first thing I would do is convert all the coefficients to base 3. -3 is a drop down, everything else is a drop down. 9 can be rewritten as 3 to the power 2, everything else is a drop down. 27 can be rewritten as 3 to the power 3, everything else is a drop down. 81 can be rewritten as 3 to the power 4, everything else is a drop down. Now we really do have base 3, x, y, and z. So we're ready to rock and roll with the exponent laws simultaneously. Again, if we look at all the negatives, we can interpret the negatives as -1, and that's the first thing I do. So we put a bracket, -1 bracket, and we scan for all the negatives. We pick up a 2 here, drop it in. We pick up a -1 here, drop it in there, and on the bottom we pick up a -1, becomes +1. And we've finished with the negative. We've finished dealing with the negatives. So from now on, no more negatives because we dealt with all the negatives right here. Next, we turn our attention to the coefficients. We're looking at base 3. So for base 3, we pick up a 2, drop it in. Base 3, we pick up -2. 2 dot -1 is -2, drop it in. On the bottom, 3 dot -2 is -6, becomes +6. And 4 dot -1 is -4, becomes +4. So we've dealt with the minus sign and the coefficients at this point. Now we're going to deal with the variables. We scan the expression only for base x. So there's an x right there. We get negative 2 dot 2, which is negative 4. Drop it in. There's an x right here. 3 dot negative 1 is negative 3. Drop it in. On the bottom, we get x to the power negative 2. So we get negative 2 becomes positive 2. Drop it in. And over here, we get negative 1 dot negative 1 is plus 1 becomes negative 1. So we're finished with base x. Now we're going to do base y. There's a base y term right here. We pick up a 2, drop it in. There's a base y right here. We get 2 dot negative 1 is negative 2. Drop it in. Over here we get negative 2 becomes positive 2. Drop it in. Over here negative 1 dot negative 1. Negative 1 dot negative 1 is 1 becomes negative 1. Drop it in. And we're finished with base y. The last base is z, so we scan for z's. Over here we pick up negative 1 dot 2, which is negative 2. And over here we pick up negative 1 dot negative 1, which is positive 1. And on the bottom, over here we pick up negative 2 becomes positive 2. And over here, negative 1 dot negative 1 is 1 becomes negative 1. And so we've dealt with the minus sign over here. We've dealt with all the coefficients over here. We've dealt with base x over here, base y here, and base z here. All we have to do is evaluate these little integer strings here, and we're almost done. When we simplify those integer strings, we get negative 1 to the power 2, and then we get 3 to the power 10, and then we get x to the power negative 6, and we get y to the power 1, and we get z to the power 0. Negative 1 to the power 2 is certainly positive, so the final result would have a plus sign in front. 3 to the power 10 we can evaluate later. X to the power negative 6 is a downshift. We downshifted to the denominator. Y to the power 1 is certainly y. Z to the power 0 is just 1. That's provided z is not equal to 0. But we won't worry about restrictions right now. This is, these exercises are just some practice on using exponent laws to simplify expressions. Okay, there will be other videos in the future dealing with restrictions. Okay, that's a topic in and of itself. For the time being, we'll assume that z is not 0, otherwise 0 to the power 0 would be undefined. So we get z to the power 0 is 1. And at the end of the day, we get 3 to the power 10 dot y all over x to the power 6. Again, if you want to expand that, you can let the calculator expand 3 to the power 10. And we get 59049 dot y over x to the power 6. And we're done. Okay, so this huge mess up here got filtered down through all these steps over here to give us this as a final answer. And clearly this is much easier to deal with than the original expression. Okay, that's the whole idea behind exponent laws, is to simplify complicated expressions to obtain expressions that we can readily analyze. Okay, let's go on to the next slide. And you know what? I think I'm going to leave this for the next video. So thanks to all for viewing this video. Stay tuned for many more to come. If you liked this video, please give us a like, submit comments, and subscribe to our channels. If not, tell us how to improve it. Over and out from MathLab Tutorials in Toronto.